Good afternoon, folks. How are you today? We are in week number 12. We just started talking about ordinary differential equations. Especially, we actually solved one first order ordinary differential equation. So what was our problem? We were given a differential equation dy dx, which is a function of x and y. We also know that y at some x I is yi, and our object, these are all one-step methods, so our object is to find what is yi plus 1. So if we take one step, then we can progress from left to right. And I said we are going to do three methods: explicit Euler's method, so these are all one-step methods, as I said. So I said we were going to cover explicit method, Euler's method, which we did last time. Today we are going to look at implicit iterative Heun's method and explicit Runge Kutta fourth order method. But again, to set the stage right, we integrated this differential equation, and our key idea was yi plus 1 will be yi plus the integral from xi plus 1 of this function f with respect to x. So our key idea is how to evaluate this integral. So different methods have different ways of finding this integral. So what is this integral? This integral is area under the dy dx curve. So if this curve is like this at xi, since we know both xi and yi, we know this function value. At xi plus 1, we don't know yi plus 1, so we can't evaluate this function value. So what the Euler's method does, Euler's method says that let's approximate this strip area to be this rectangular area. So in this case, it is an overestimate. So Euler's method says yi plus 1 is yi, and this rectangular area would be h, because this strip size is h, times function at xi yi. So that's what Euler's method did. And we did an example. I hope you finished that table. So we did this example. And what we found out that local error was proportional to h squared. That's error in estimating area of one strip. So if we have n strips, our global error, always one order down, would be proportional to h. But notice we do just one function evaluation. One function evaluation. So that's the key idea of Euler's method. The reason we worry about function evaluation is usually in real world problems, this is the most expensive computation function. Because remember, it could be a black box, that function, and could be very expensive. Okay, so let's look at Heun's method. We say Heun's method is an implicit method. Implicit means basically that it is iterative. We just don't have a simple formula that we go ahead and calculate. It is also called predictor-corrector type of method. So what we do is we predict a value of yi plus 1. Let's say this is yi plus 1 predicted value. Then we have some method to modify it and we get what is a corrected value. And then we say this becomes our predicted value. We modify it further, correct it further, and we keep on doing this till we have a match. So let's look at our procedure. First, we look at it graphically. Okay, so here is our dy dx. Remember, we want to find area, the strip area. And this is our y curve. At xi, we know yi. And if we knew the strip area, that strip area would be this distance. So what the Euler's method did was it did a rectangular estimation. So obviously that is an overshoot. So that becomes our predicted value, yi plus 1 predicted. So using this predicted value, then we guess, now that we have a yi plus 1 value, we find out what is the dy dx there. And what we do is really average the two. So in effect, what we are doing is we are drawing a trapezoid like that. So then we use the trapezoidal area, which is of course better, and that's our corrected value. And we keep repeating this process. So let's look at it in an algorithmic way. So first step, we calculate a yi plus 1 predicted value, which is yi plus h times function at xi yi. So this is our Euler's estimate. And then what we do is we compute the slope. Which is function at xi plus 1 using this yi plus 1 predicted value. And then what we do is average the slopes. So we calculate y prime average, which is yi prime plus this yi plus 1 prime. And then use this average slope as our corrector. So this was step 2, step 3, step 4. yi plus 1 corrected is yi plus h times this y prime average. And then we compare this predicted value and corrected value. So how many ever digits we match we need. If we don't get it, then what we do is we say this yi plus 1 predicted value The new value is this corrected value, and we keep repeating. So we iterate if we don't converge. Okay. Okay, so let's do an example. So we'll take our same problem. We are given that y prime, which is our function of xy, is square root of x plus square root of y. Y at x is equal to 0 is 1. We will use h is equal to 0.1. So we start doing Heun's method and we tabulate. So this is xi, this is yi. Then we'll compute the function at xi, yi. Then we'll get our yi plus 1 predicted value. Then we'll compute the next slope using this predicted value. And then we'll get a corrected value. And we'll decide have we converged or not. Okay. So x is 0, y is 1. We compute our function square root of 0 plus square root of 1. So we'll get 1. So y plus h times 1, we'll get 1.1. Now our next x value is 0.1. So we are going to compute this function square root of 0.1 plus square root of 1.1. And I'm going to keep 6 digits because I want to do a few iterations. 1, 3, 6, 5, 0, 3, 7. Please do it with me. Okay, so now we have this function value. We are going to average the two. So 1 plus 1.365037 divided by 2. We are going to multiply it by 0.1 and add 1 to it. So we will get 1.118252. So you can see that we are matching one correct decimal digits right now. So let's say we are not converged. So then this corrected value becomes the predicted value. We compute the function at xi plus 1, 0.1, x and y is this value, and calculate the function again. And we'll get 1.373702. Then we average these two function values times 0.1 plus 1, and we will get 1.118685. So now notice we have matched 3 decimal digits. If you are not happy, we can go once more. So now this corrected value becomes the predicted value, and we recalculate the slope there. So we get 1.373907. Again, we average this function with 1 times 0.1 plus 1. And now we get 1.118685. And now I match all 6 decimal digits that I have been keeping. I can't improve any further. So let's say I've converged. So at 0.1, our x value is 1.118685. All right. I would like you to do one more iterations and see if you match my values here. Okay, remember, keep 6 digits, decimal digits. Okay, so Heun's method. First of all, local error is proportional to h cube. Remember, we are making the trapezoid. Global error is proportional to h square. In number of function eval, we are doing at least one to get predicted value, at least one to get corrected value. So even if we converge in 2 iterations, we require 2 or more function evaluations. So sometimes this can be expensive and there might be better methods. But in any case, you can see since the truncation error is better than Euler's method, if this was the true solution, of course, Heun's method would give us better solution than Euler's method. So because of this uncertainty in number of function evaluations, this Heun's method is not a very popular method. So our next method is Runge-Kutta fourth order method, and this is by far the most popular method in solving differential equations. Okay, first of all, this is an explicit method. So we just do a series of calculations and we get our answer. So what it does is it does weighted average of 4 area estimates. That's why it's called fourth order method. So let's see how it does that. So again, let's see it graphically first. So this is our dy dx. So remember, this is function of x and y. At xi, we know this function value. At xi plus 1, we want to find yi plus 1. Then we will be able to get this value. So we need to find the strip area. So what Runge-Kutta method does is it says, okay, let's use that rectangular area. That is our first estimate. Using this rectangular area, we predict yi plus 1, just like we did in Heun's method. Using that, we can calculate the slope. So let's say we get the slope here. So what we do is, instead of predicting the slope at the right end, using the same extrapolation scheme, what we do is we instead predict the slope middle of the strip. And we build another rectangle. So using that rectangle, we get K2. Then using this new area, we again predict the value in the middle, the slope value. Let's say it comes out here. So we build another rectangular area, K3. And finally, using this third rectangular area, we predict the slope at the right end this time. So notice we built one on the left rectangle, two rectangles in the middle, and then using this right end, we generate the fourth rectangle, and that's our K4. So whatever I have said graphically, let's repeat it. So K1 is just this rectangular area. So which is h times function at xi, yi. K2 is h times function in the middle. So it's xi plus h over 2. We would have used yi plus k1 as our estimate. Instead, we are going to use yi plus k1 over 2. Okay, k3 is h times function, again in the middle. Ordinarily, we would have added k2 to yi, but we want yi in the middle, so we are just going to add k2 over 2. Okay, k4 is h times function, and remember this time we are building the rectangle on the right hand side, so we will have xi plus h and yi plus k3. We are adding the whole rectangle. And then we do a weighted average. We say yi plus 1 is yi. We give 1 unit of weight to k1, 2 units to k2, 2 units to k3, and 1 unit to k4. Divide by 6. Now you may recognize something. This is what we did. So imagine Simpson's 1/3 rule, and we have split this whole strip into 2 mini strips. So what did we do? We gave 1 unit of weight to left, 4 units of weight to middle, and that's where you see 2k2 and 2k3, and 1 unit of weight to k4. So this is like Simpson's 1/3 rule. So in Simpson's 1/3 rule, you may remember local error was proportional to h to the power 5. Global error proportional to h to the power 4. Number of function evaluations. Obviously, we have 4 area estimates, so 4. All right, so we are going to do our example. So we'll use the same example problem that we have been working with. And please work along with me. So we are given dy dx, which is a function of xy, is square root of x plus square root of y. Y at x is equal to 0 is 1. We are going to use spacing of 0.1. So here is our tabular form. So we are going to do xi, yi. Then we are going to do 4 estimates, k1, k2, k3, k4. Okay. At x is equal to 0, y is 1. So even though I have a table, I'm going to write out longhand for the first iteration. So what is our k1? H times function, and our function is square root of x plus square root of y. So we will get 0.1. Our k2 is 0.1 h times square root of x, which is 0 plus 0.1 over 2, h over 2. And y is y plus k1 over 2. Okay. So this time I want you to keep 6 digits. Okay. So that was k1, 0.1, k2, 0.124830. Okay. So x plus h over 2, y plus k2 over 2, okay? So let's do 0.1 times 0.1 over 2 square root plus 1 plus 0.1248030 divided by 2 square root. So we will get 0.125434. Okay. All right. K4. So let's copy this. So this will be 0.1 times square root of 0 plus 0.1. Remember, we are on the right of the strip. 1 plus 0.125434. Okay. So we will get 0.137709. Okay. So at x is equal to 0.1, we are going to do a weighted average. So 1 unit of weight to this, 1 unit of weight to this, 2 units of weight to these. So 0.1 plus 2 times 830.125434 plus 0.137709 divide by 6, and we add 1 to it. So we will get 1.1230, and I'm going to round this up to 50. Did I do it right? Let's try it again. 0.1 plus 2 times 0.12483 plus 2 times 25434 plus 0.137709 divided by 6 plus 1, 1.123040, sorry, not 5040, rounded up. Okay, so I would like you to do a couple more iterations. See if you can match my answers. I'm keeping more digits, but you can round them up to 6 digits. Okay. Okay, so let's summarize what we have done so far. So for one first order ODE, we looked at 3 methods: Euler's method, Heun's method, and Runge Kutta method. We found local error. This was order h square, order h cube. This is order h to the power 5. Global error, order h square, and order h to the power 4. Number of function evaluations, Here we have 1, here we have 2 or more, here we have 4. And it turns out this is the most preferred method. However, remember this can be a huge tax often. So we have to compromise. Okay, so let's stop here.